I'm Dr. Chinna Dastagiri Goud, Assistant Professor, Department of EEE. So, today we are going to discuss about the DC generator EMF equation. So, this is under the course EEE. So, as we know, we already discussed about the DC machine construction. So, machine either generator or motor. So, DC machine have same construction. So, here today we are going to discuss about the EMF equation of this DC generator. We already seen the construction of DC generator and then we went through the principle of operation. Then we seen the dynamically induced EMF equations. Now we are going to see complete EMF equation of DC generator. As I said before, whenever EMF will come, EMF, electromotive force. So whenever EMF will induce or electricity father of electricity, Faraday's equations are very, very important. So he has two equations. One is Faraday's first law is saying how EMF will induce. When a conductor cuts the flux, it will induce the EMF. That is the Faraday's first law. And Faraday's second law, how much EMF will induce. So, the induced EMF is equal to the rate of change of flux. These are the two main laws we will utilize while we are explaining the operation of the generator wherever EMF is induced. And then we also will say that how much EMF is induced. So, for the same formula, we will derive the different equations for the synchronous generator, induction generator and transformer and the DC generator. So, today we are going to see the EMF equation of DC generator. So, first we will consider our DC generator constructions. So, I am considering that, let us consider the DC generator has P number of poles. So, P is equal to number of poles. So, as we already seen that and discussed that the main principle is electromagnetic conversion. So, definitely there will be electrical circuit will be available and the magnetic circuit will be available. So, magnetic circuit means poles will come. So, P is equal to number of poles and phi is the flux per pole. So, flux per pole will measure in the Webers. So, units are very important while doing the numerical problems. A flux per pole is in Webers. Then we will consider the number of conductors. We want the conductors also. So, Z is the number of conductors. So, we already discussed that these conductors connected in a proper manner. So, that is why the complete conductors set is known as armature winding. So, this winding has two types of winding with two different dimensions, and we also discussed that number of parallel paths. So, I am considering A is the number of parallel paths. Okay. So, along with this one, we have to know that there should be some motion, mechanical energy we are giving because armature has to cut the flux. So, we will consider that this armature is moving with a speed of N. So, N is the speed in RPM. What is the RPM? Revolutions per minute. It is the revolutions per minute. Okay. So, finally, we will consider the EMF induced is E. So, this is the EMF induced in the generator. So, now we will go to the concept. So, we consider the P number of poles. So, for understanding purpose, I am taking there is two number of pole structure. So, I am drawing that. So, two poles. So, one is the north pole. So, definitely we know poles will be in even number. So, I am considering this is my north pole. And I am considering another, that is my south pole. So, it is a two pole machine. I am considering another is my south pole. So, this is north pole and this is south pole, and flux will flow from the north pole to south pole. And now I am considering my armature. So, this is my armature. So for understanding purpose, right now I am taking only one conductor. So I am taking one conductor which is available here. Suppose you consider this is my conductor. So which is moving in the clockwise direction, with the speed of n, So with n RPM it is rotating, and the flux per pole is phi. So I have to know now what is the EMF equation. So what we know from Faraday's first law, when a conductor cuts the flux, an EMF will induce in it. And what is Faraday's second law is saying? It is saying that how much this EMF magnitude. Faraday's second law, the induced EMF is equal to rate of change of flux. So technically we will say in mathematically E is equal to d phi by dt. So d phi by dt. So this is the EMF induced according to the Faraday's law. So here we have to find out the EMF equation, this EMF equation for DC generator. That means we have to find out what is the change in flux when it is moving and how much time it is taking to change that flux. So here first we will observe what is the meaning of change in flux, how much it is changing, and then we will see how much time it is taking for changing the flux. So as we know our equation, they are saying that E is equal to d phi by dt. So now what we have to find? Change in the flux. First we have to know change in the flux. What is the meaning of change in the flux? When it is moving, it is cutting the flux. So definitely the flux will changes in the conductor. So we will observe it, how it is going to change. So again I am considering my two-pole machine. So this is my north pole, and this is my south pole, and this is the conductor, armature. So in this one we are going to take one conductor. So this is the conductor. So we know that as a flux will come out from the north pole, and it is taken into the south pole flux lines. So conductor is moving, so the flux per pole is, this is phi. Okay, so here I am considering direction also I am considering. So flux is coming out, I am considering as a positive flux. Coming, it is taking, I am considering this is as a minus phi. Okay, so now the conductor is under the flux pole. So I want to change what is the flux changes. So I will consider what is the flux changes when it is moving. So it is started moving. This is my conductor. This conductor is started moving. So it is moving from this place to this place. So now here what is the flux? Phi. Here the flux is minus phi. So what is the change in flux from there to there? So phi minus phi. So that is equal to 2 phi. So here the flux is phi. When it came to south, it is came to 2 phi. So the change in the flux is phi. Difference is phi. Here 2 phi, it is phi. So the change in the flux is phi. So similarly, it is moving from this point to this point to this point. So here now already its flux is 2 phi. So here the flux is phi. So what is the change in flux? Phi minus 2 phi is equal to minus phi. So flux is reduced to the phi. That means magnitude is same. The change in the flux again is phi. So we will see that, we will consider that in a revolution, what is the d phi? Change in the flux will take as a phi. So for our EMF derivation, what we are considering, the change in the flux d phi of the conductor. One conductor we are inducing the EMF. We are inducing the, first we will calculate single conductor EMF, single conductor induced EMF. So that is equal to d phi by dt we have to calculate. So I am considering this is E1. So change in the flux d phi is phi. Change in the flux d phi is phi. So I hope everybody is understand how the change in the flux we calculated. Now we will go that how much time it taken. How much time it is taken. So our second task is we have to find out time taken to change the flux, phi. So phi flux change, how much time it is taken to change the flux phi. That means how much time taken from it come to north pole to south pole and from south pole to north pole. Right? So how much time it is taken. So we will consider, we already know that it is running at n revolutions per minute. N revolutions per minute. That is the n is equal to RPM we taken. Per minute means 60 seconds. Every time we have to take in SI units, we are taking in 60 seconds. So in one revolutions, how many times it is changing the flux, we will see. So one time it is changed from north pole to south pole, and again it is changing. So here if you observe, it is taking from north pole to south pole. When it is taking, one time it is changed the flux, from south pole to north pole 2 times. That means if 2 number of poles is there, it is changed 2 times. If suppose 4 poles are there, so if 4 poles are there, here one north pole will, here one south pole will come. This is north pole, this is south pole. So just we will see. So how it will be. So suppose those 4 poles are there, I am drawing here. So this is my 4 pole machine. So this is north pole, this is south pole, this is north pole, this is south pole. So conductor will move from this point to this point. One time flux changes, again one time flux changes, again one time flux changes, again one time flux changes. So this is plus phi, this is minus phi, this is plus phi, this is minus phi. And if you change the flux chain, phi minus phi, it will become 2 phi. So changing the flux is phi. Again it will come from this place to this place. Phi minus 2 phi, that is equal to minus phi. Again it will change the flux. Again it will go from the minus phi. Okay. So here it came. Sorry, we have to consider what is the flux change from this point to this point. So phi minus phi, it will take phi minus of minus phi. It will become how much? 2 phi. So again it will go to 2 phi minus phi. It will become phi. So here the thing is, flux changes from one point to another point. It will become the phi. Phi is the changes. Okay. So from each time, how much it is changing? Phi flux is changing. So here also plus phi, it is coming towards the conductor. It is going outside the conductor, towards the conductor, outside the conductor. So here what we understand from this one. So the change in the flux, will be poles times. So P number of times it is changing the flux for 1 revolution. That means how many times it is changing? The P times it is changing. So each revolution. So that means in 60 seconds, that means 1 revolution is 60 seconds. How many times the flux is changing? Pn times. Pn times flux is changing in 60 seconds. Why? In n revolutions per 1 minute. So in n revolutions, Pn times flux is changing. So Pn times in 60 seconds. So for 1 revolutions, how much time it is taking? Because in 1 revolution only, it is taking 5 flux is changing. So for 1 revolutions, it is taking 60 by Pn seconds. So this is our dt. So time taken to change the flux dt is equal to 60 by Pn seconds, right? So now we have d phi, now we have dt, so we can know that the EMF induced by the single conductor, EMF induced by the single conductor. So the EMF induced by single conductor is given as E single conductor is equal to d phi by dt, which is equal to phi by 60 by Pn. So Pn will come upside, so it will be P. So we can write P phi n by 60. So what is this? This is the EMF induced by the single conductor. EMF induced by the single conductor. So but how many conductors we have? We have z number of conductors, but we have z number of conductors. Right? So if z number of conductors are there, all are in series. If all are in series, EMFs will add. So each conductor will induce, if conductors are in series, suppose this is the conductor 1, this is the conductor 2, and this is the conductor 3, and this is the conductor 4, and so on. Suppose EMF induced by the conductor 1, is small e1, again this is small e2, and this is small e3, again it is small e4, and so on. So what will happen? The total EMF induced is, we have to add. So what we will do? E is equal to E1 plus E2 plus and so on. How much conductors? Suppose N conductors are there, Z conductors are there, so E into Z. But here the problem is armature winding, all the conductors are not connected in series. We seen that. So armature conductors are connected in two types. One is lap winding, already we discussed about these things. Another one is wave winding. So the problem is, in lap winding and wave winding, how they are differ is, there are number of parallel paths. So the parallel paths in lap winding, is equal to number of poles. Whereas the parallel paths in wave winding is equal to 2. Whatever it is the number of poles, the parallel paths is 2. Why we are considering parallel paths? As we discussed previously, suppose two conductors are there in parallel. Okay, these two conductors are there in parallel. So this conductor will generate the EMF E1. This conductor is generated the EMF E1. So the total EMF we will get is same. E1 only. It is not E1 plus E1. So that's why if parallel paths is there, we should not consider that induced EMF to add, because it is same. So parallel paths are there. If total number of conductors are Z, then in lap winding and wave winding, the number of conductors will divide. So in lap winding, what will happen? So lap winding, Z number of conductors are available. So number of series connected conductors, is equal to Z by P. Y means all Z conductors has to divide between the P number of parallel paths. And similarly, in wave winding also Z number of conductors. So number of series connected is equal to Z by 2. Z by 2. So we don't want to two equations for our EMF equation. So we commonly given that we consider A is number of parallel paths. A represents the number of parallel paths. Therefore, what we'll get? We'll get A is equal to P if lap winding and A is equal to 2 if it is wave winding. Okay, so now we got the clarity how many conductors are connected in series. So from the previous slide, whatever we see in the previous slide, we told that this is for one conductor. So how many number of conductors connected in the series? So all the conductors will consider that equal EMF they are inducing, because the same type of material we are using. So we will consider that multiply with the number of series connected conductor. So finally we will get the EMF of, so finally we are getting the EMF induced in DC generator. E is equal to P phi N by 60 into Z by A, which is equal to P phi NZ by 60 A. P phi NZ by 60 A. Right? So this is the EMF equation of DC generator. So while simply this is the explanation of DC generator, how EMF equation will derive. So simply if you want to write in exams, so we will go with conclusions what we discussed up to now. Simply I will write here. So consider a DC generator. Okay. So with P number of poles, P is equal to number of poles. Z is equal to number of conductors. Phi is equal to flux per pole. N is equal to speed in RPM. A is equal to number of parallel paths. In armature winding. And E is the EMF induced. Okay. So let us now for understanding consider a single conductor. The EMF induced is E1. So how we will calculate? From Faraday's second law, E1 conductor is equal to d phi by dt. So for understanding purpose, what we taken a diagram. So we will take two pole machine. This is the north pole, and we take another pole. It is the south pole. Flux is coming from north to south, and consider a armature consider a armature, and we have a armature and one conductor. Okay, conductor is moving in clockwise direction. So this is the flux and this is the speed. This is the speed. So from the DC generator, flux changes from one pole to another pole is phi. Therefore, d phi is equal to phi. D phi is equal to phi. This is the second equation. So we will consider this is the first equation. Okay. Then time taken to change flux d phi is dt. So which is equal to 60 by Pn seconds. So as we know, Pn times will change in 60 seconds. So one time to change the flux. So it is 60 by Pn. So this will be our third equation. From equations 1, 2, 3, E1 conductor is equal to d phi by dt, which is equal to d phi we are substituting from the equation 2, that is phi by 60 by Pn, which is equal to Pn phi by 60. So this is the EMF induced in one conductor. Now in a DC generator, Z number of conductors. In a DC generator with Z number of conductors, connected in a number of parallel paths, then EMF induced is E is equal to, for one conductor, E phi n by 60 into total number of conductors with number of parallel paths is Z by A. So this is P phi n Z by 60 A, where Z by A is number of series connected conductors. So finally we derived the EMF equation of DC generator, that is E phi n Z by 60 A, where P is the number of poles, phi is the flux per pole in Webers, n is the RPM, speed in RPM, Z is the number of conductors and A is the number of parallel paths. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.